Okay, so now we have an inductor problem, and so we're going to use our inductor equations. So what we know is that I of t equals I at infinity plus I of 0 minus I at infinity e to the minus 1 over tau times t. We know that tau for an RL circuit equals L over R equivalent. It's asking us also in one of these questions for voltage, and voltage equals L di dt. I don't think I had that on our first page. I didn't. So voltage equals L di dt. All right, and so it says the switch was in position 2 for a long time. Oh, and then also to remember, for inductors, it's current that can't change at 0. So we're looking for current at 0 minus. Will tell us what current at 0 is. So, but voltage can change instantaneously. So we were in position 2 for a long time. So let's draw that. Okay, so under DC conditions, an inductor acts as a short circuit. And so it looks like this. Oh, that's really a good resistor. So it looks like this is what we have. Now you'll notice, let's see, V is 12 volts. R1 is 30 ohms. You'll notice that since it's been a long time, the inductor is acting like a short circuit, which means it's shorting out this resistor. So at t equals 0 minus, we really have a very simple circuit. We just have a voltage source and a resistor. And the current through the inductor is the current in that circuit, except oh, I'm just doing it in a different order. Okay, so so V equals IR, where 12 equals I times 30, where I equals 0.4 amps. So this is I of 0 minus. Okay, so we're also supposed to find VL of 0 minus. Well, at 0 minus, there's a current flowing through this inductor right here. And on a straight wire, there is no voltage change. There's no voltage difference on different parts of a wire. So that's just 0. VL of, so I of 0 minus is 0.4 amps, but VL of 0 minus is 0 volts. Now we want IL of 0 and VL of 0. Well, IL of 0 is easy. We know that IL of 0 has to be 0.4 amps because it can't change. VL of 0, however, can change, and we want to find that from our new circuit. So if you're ever trying to figure out, what to do with one of these problems, so for a capacitor, if you're trying to find the current at 0, go with 0 plus. For an inductor, if you're trying to find the voltage at 0, go with 0 plus. For a capacitor, if you're trying to find the voltage at 0, go to 0 minus. And for an inductor, if you're trying to find the current at 0, go to 0 minus. Okay, so whatever I just said, I hope was right. And now I'm looking for VL of 0, and I'm looking for the current. I'm looking for the voltage at 0 and that's after the switch has been moved to position 1. So and this was, for me, particularly tricky. So I hope I can explain it well. Okay, so tricky because I don't find it intuitive that things would work this way, but this is how it is. The one thing we know for sure is that current through an inductor cannot change instantaneously. So I know that. And so with that, you want to grab hold of those parts. That current through an inductor can't change instantaneously, voltage across a capacitor cannot change instantaneously, and use it. So I know my current right here is 0.4 amps. And I know that the inductor is in parallel with R3 and R2. So if I can get the voltage across R3 or R2, then I will know the voltage across the inductor. Okay, now this will be 0. So notice the current is going to come here, and then we'll have current division. I'll just find the current through R3. You can find the current through R2, but I just need one of them. So it'll be the total current. So this is the current through R3, is the total current times the value of the other resistor. So this is current division. The other resistor was 120 over the sum of the resistors. R3 is 60, so this is 180. And this is 0.2667. Okay, now I'm going amps. I'm going to use that to find the voltage across R3. So the voltage across R3, well, I'm going to write it in a certain way that maybe will help. I'm going to call this ground, and I'll call this V up here, because I have my current going up. And so my current is going to equal 0 minus V over R3. So 0.2267 equals minus V over R3, I think was 60. Or V equals, V of 0 equals negative 16 volts. Okay, so I find that tricky. So what you have to do with these problems is to remember to start with that given piece of information that the current can't change instantaneously. So you start with that. You say, I know that, and then work from there. Because other things seem like they might be a certain way without using that. Okay. Now we want IL at infinity and VL at infinity. So at infinity, this is just like as if we had a capacitor with no source. There's no source in here. Eventually the inductor is going to discharge, and our current through it will be 0, and also our voltage across it will be 0. So that's at infinity. So IL of t, this is where we use that equation that we have been, well, we were using the capacitor version, but the same one really. I at infinity plus I at 0 minus I at infinity e to the minus 1 over tau times t. Oh, we have not found tau yet. So tau for an RL circuit, tau is L over R. And we can look at our circuit that we have right here, and we can see that R equivalent is R2 in parallel with R3. That one is pretty easy to see, that one. R equivalent is 120 times 60 over 120 plus 60 . Which is 40. And then tau is L over R. L is 0.2. R is 40. So tau is 0.005. And 1 over tau is 200. So IL of t equals I at infinity, which was 0, plus I at 0, which was 0.4, minus I at infinity, which was 0, e to the minus 200t. IL of t equals 0.4 e to the minus 200t.